Okay, so we are here today for the second talk of Professor Edward Lee from the University of California at Berkeley. So last time Edward presented to us the PRET machines that deliver deterministic timing at the hardware level. But today we are going to move up in the system stack and focus on the programming level. More precisely, Edward is going to present Lingua Franca, a deterministic and concurrent polyglot coordination language that can be used to design cyber-physical applications. So, Edward, the stage is yours.
Thank you, Mathieu, and thank you everyone for being here. This is actually, I realized as I was preparing this talk that this is actually the first time that I've attempted to give a talk about this whole project, which is kind of a multifaceted project with a lot of aspects to it. Many participants in this project that I owe a great debt to, so I'm going to be representing their work much more than my own. But hopefully you will be able to share some insights with you and share the excitement that I have with the project. So first, the context of the work. My focus is very much on cyber-physical systems, so it's about networked computational elements that are interacting with physical processes, and those are the ones, if it's just information technology, it's not so interesting to me. It's got to have some physical dynamics involved in the system. And so that's the context in which we'll be working. Now, a big part of the focus of this project is on deterministic concurrency, and that's not a new problem, nor is the solution space small for this. There's a tremendous amount of prior work in this area, dating back 50 years at least. And a lot of it is very, very much informs this work, in fact. And so I, again, owe a debt to a tremendous legacy of prior work there. So even though there's a long history of work with deterministic concurrency, the fact is that non-deterministic methods dominate. Most of the people who are out there designing systems are not using these deterministic techniques. Now, that might, I think that's probably not a surprise to people in the room here, even though you're probably among the exceptions rather than the rule here, who have embraced this idea of getting better determinism. But the fact is that when you go to people who are working in practice, the techniques that they use tend to discount the value of deterministic mechanisms, and I'd like to look a little bit at the reasons for that. All right, so let me talk about some of the popular techniques. So one of the ones that is very widely used in cyber-physical systems these days is publish and subscribe. The ROS robot operating system programming environment is a very popular example of a software architecture framework that uses pub/sub. MQTT is another one that's pretty widely used in Internet of Things applications. And there's various cloud versions like Azure and Google Cloud that have this pub/sub mechanism in it. And so what is this about? Well, components publish events on topics, and other components subscribe to those topics. And this is a tremendously convenient programming model. It's very easy to use. It's very intuitive, and message handlers get invoked in the subscribers, but the essential non-determinism problem is that there's really no ordering guarantees about the messages, particularly when you have messages coming from different publishers on the network and they're converging on a single subscriber. There's no semantics to the ordering in which messages get handled. Now, the question is, well, is this a problem? Well, often it's not. So I worked with then a PhD student at UT Dallas, who subsequently became a postdoc in my group, Sarush Bateni. He took a very close look at a fairly large ROS-based application that is quite popular out there among people who are working on autonomous driving. So this is an open source full stack autonomous driving framework called called autoware.auto, and it it's built on ROS, and it's been deployed on vehicles. When you download AutoWare.auto, you get a interface to a simulation environment called LGSVL, which is a pretty popular simulation environment for people working on self-driving cars. And there is an application that is distributed with this that is a valet parking, an autonomous valet parking application. So the idea is you drive up to some entrance, get out of your car, tell your car to go park, it goes and parks. Okay, so the picture of the ROS architecture is shown on the screen here. These are all ROS components, and the connections between them, for the most part, are publish and subscribe connections. And I'm going to focus particularly on the interface between the LGSVL simulator and the behavioral planner. The simulator here has an interface that is meant to exactly match the interface that you would use in a real car. Okay, so the commands that go to the LGSVL simulator are the same commands that you send to the hardware in a car to make it do something. Okay, so that's the context that you get when you download this thing. So Sarouche took a look at this interaction between the LGSVL interface, and in particular found that there were two publish and subscribe channels that were being used to communicate between these. And there was a good reason why there were two channels, because the software architecture naturally decomposed into a hierarchical system so that these two sources of information were really, really disjoint. So one of these channels was reporting the state of the vehicle, and in particular one part of that state is whether it's in forward gear or in reverse gear. And another channel was being used to report the vehicle kinematic state, which is its velocity, includes, among other things, its current velocity. And he looked at a sequence of commands where you put it in forward gear, you see a forward kinematic state, you put it in reverse gear, and you see a reverse kinematic state. And he found that if you ran a large enough number of experiments with this, even in very benign network conditions, you would see all four permutations of these messages. So in roughly 300,000 tests under benign conditions, he found that you would see things out of order, which meant that you could get into a situation of mode confusion where the car thinks it's in reverse gear but is moving forward, or it thinks it's in forward gear but is moving in reverse. Now, if the car were actually doing that, that would probably be indicative of a pretty serious problem, like an accident has happened, and so, what should the vehicle controller do when it sees that state, right? Should it deploy airbags or do something drastic? In this case, though, the ordering of these messages is simply a consequence of the pub-sub bus, and the fact that the messages, that the vast majority of the time the messages arrive in the expected order, means that you're not likely to see this problem in testing. You can test the system quite a bit, and you won't see this reversal of messages. I mean, Sarouche had to run it for quite a long time to see this reversal, but he saw it very predictably. As long as you ran it sufficiently, you would eventually see this mode confusion event happening. So he took and ported this whole autonomous driving stack to Lingua Franca using the ROS components as they existed. So he didn't rewrite the ROS components, he just rewrapped them as Lingua Franca components, and showed that for under similar conditions, very large numbers of runs never resulted in this mode confusion. And that was because of the deterministic semantics of Lingua Franca compared to the pub-sub bus. So let's look at some other popular techniques. So for example, service-oriented architectures are pretty popular these days. gPRPC is a framework that's pretty widely used. AUTOSAR, which is very widely used in automotive technologies, is a service-oriented architecture. So in a service-oriented architecture, a service is a procedure that's exposed by a component, and components can invoke services on other remote components. And callers can wait for the results. It's a synchronous invocation of the service, or they can retrieve results later using a technique called a future. Typically, the service invocations are mutually exclusive, but once again, there's no ordering guarantees. And so if you have two different clients requesting services from the same service provider, there's no semantics to the ordering in which those services will be provided. So once again, another very talented PhD student that I have been working with actually now for several years. He's a PhD student at TU Dresden, Christian Menard. He took an application which is an ADAS, Advanced Driver Assist System, that is distributed as a reference application along with the AutoSAR framework. And so, again, it's just, using the demo programs that are provided by the framework providers. And he found similar problems to the kind of problems that Soroush found. And again, with relatively low probabilities, you would get similar kinds of mode confusion that would result in the ADAS system potentially seriously misbehaving. And you could say, okay, well, the ADAS system is in some sense it's a safety critical system, but in some sense it's an overlay on top of the existing control system in the car. So ADAS is used for braking assistance is one of the key things, and widely deployed. Any modern car, or many modern cars, have these vision systems, for example, that will detect pedestrians in front of you and automatically brake, or measure distances to obstacles and do automatic braking. And you might say, well, there's a certain safety critical element to this, but maybe you're just better off if you just, when in doubt, apply the brakes, right? I mean, a stopped car is safer than a moving car. But that's not necessarily the case, right? So I'm going to show you an accident that happened in November of last year with a Tesla. The Tesla just turned on its turning signal, shifted into the left lane and stopped. And it created a pileup with a whole bunch of cars crashing into it. Okay, this is what the pileup looked like from the back. And there was no obstacle in front of this car. And so you have to assume that this was essentially a software bug. And it could very well have been caused by some sort of mode confusion scenario. Tesla will never tell us, of course. What about shared memory? Well, shared memory is very widely used. People use threads, but there's also more sophisticated distributed shared memory techniques that you can use. These are often justified by control system engineers under a principle that is, easy to understand from a control system perspective, which is that you always want to use the most recent data. Right, a control system engineer likes that because in control systems, latency in a feedback loop is a problem. Right, the more if you increase the latency in a feedback loop, it can lead to instabilities in the feedback loop, and so control system engineers will use this as a justification that always use the most recent data. So this is a style of design that I have come to call the Toyota style of design, where you have a whole bunch of threads running, all communicating through shared variables. Every thread just uses the most recent value of the shared variable. So you may know that a few years ago Toyota was involved in this investigation because there were a bunch of alleged incidences of unintended acceleration. This is one of the consequences of one of these incidences. This car was being driven by an off-duty police officer who had training in high-speed driving, and he was unable to control this car. And NASA commissioned a study of the Toyota software. Toyota was forced to expose all of their software to the participants in this NASA study. And the participants in the study were unable to find a smoking gun. They couldn't find the exact mechanism in the software that could have led to unintended acceleration. But they did conclude that the software was untestable. And it was untestable specifically because this policy of always using the most recent data meant that the number of correct behaviors of the software under the semantics of the program was so vast that no amount of testing could ever cover all the possibilities. Okay, so this is a problem with this principle with shared memory techniques. So let me talk about another popular technique these days. This one is particularly popular in cloud computing and situations where you have multiple CPUs communicating over networks. This is actors due to Carl Hewitt and Gulaga from way back. So actors are concurrent components that communicate by sending each other messages, and it's a fairly straightforward model, which is one of its key attractive features. You can use it very easily. So one of the key way that it works is that you have an input message queue, and you receive messages over the network, and then you have message handlers. So the messages can include in the header a request for a particular kind of handler. So the messages can have kinds, you can have different handlers. Okay, but once again, a key problem is that if you have messages originating from multiple sources on the network, there's no semantics to the ordering of the messages, and so the order in which your handlers get invoked can be non-deterministic. So let's look at a really simple example of an actor program. So this is a program that has some internal state, in this case just an integer, and it has two handlers, one that will double the value of the state and one that will increment the value of the state by some argument. Okay, so the idea is you've just got these two operations that you can do on a state variable, and then you have a client that in this case is going to just, it creates an instance of that actor, and then it sends it a double message to double the value of the state, and then sends it a message to increment the value by 1. Now, when you compose these two, like this, under certain benign circumstances, you will get deterministic behavior. So for example, if the communication between these components uses TCP/IP, which does in-order guaranteed delivery, then you get an overall deterministic program where the doubling occurs before the increment. Okay? But let's make a very minor innocuous change to this program where you introduce a third component that just forwards its message. Okay, so you invoke its pass message handler and it calls double on the component. Okay, so now you have a topology like this where the double message is going through this pass-through component. Now, there is no semantics to the ordering in which the doubling and incrementing will happen at this component. They could happen in either order, and in any of the popular actor frameworks that you can use today, download them and try them, and you'll see that with this architecture, you're going to get non-deterministic ordering of these operations. So is this really a problem in practice? Well, let's look at a very practical problem. Suppose you want to automate the opening of a aircraft door, okay? What's involved in opening an aircraft door? Well, it's a little more complicated than opening a door to this lecture hall, for example, because if you open the door to the lecture hall here, you don't deploy automatic escape slides that inflate. All right, so the door has two states. It's either armed or it's disarmed. And if you open it when it's armed, the slides will deploy. Okay, so typically when you're at a gate and there's a ramp outside, you don't want to open it while it's armed. You want to disarm it and then open it. Okay, so the order in which the disarm and opening happens is pretty important. So let's look at a software architecture. We got a door control. We're going to put a little microcontroller in the door, and it's going to receive messages over the network, disarm and open. And you probably do want to separate these messages because you might have, for example, a fire detection system that wants the door to open regardless of whether it's armed or not. Okay, and you might have an embedded vision system. Today, that embedded vision system is done by humans. All right, when the pilot says, flight attendants disarm doors for arrival, the flight attendants look out the window and they're required to visually identify a ramp adjacent to the door before they disarm it. Okay, that could be automated with a vision system today that determines that there is a ramp, and when a command is issued to open the door, you would choose to either disarm it first or not disarm it first, depending on whether there is a ramp outside the door, right? So one could easily envision trying to design this kind of system. The fact is, that this kind of system will potentially fail with all of these popular techniques. Okay, and the failures could be really quite drastic. They could result in a scenario like this, okay, where the slides get deployed when when you're at a ramp. And when these slides deploy, you do not want to be there. Okay, this is a safety critical problem. So if you try to design this using actors, you might have a relay component that is just the vision system that is checking to see whether there is a ramp there. So when an open command is issued on pub sub bus, this guy sees it and decides whether or not to disarm the door. But the problem is that when you compose this, then you really have no assurance of preserving the ordering of the system. So with that motivation, all of these popular techniques that are widely used today in practice, in the cars that you drive today, they have flaws. And we believe that these flaws are completely fixable. And this is where the Lingua Franca project comes in, all right? And the idea of deterministic concurrency is to give a framework where you can design these kinds of systems very practically, very competitively, and not run into these same kinds of problems. It's not that you're not going to run into fault problems. Any engineered system can fail for a variety of reasons, right? What you want is a system where it doesn't fail for accidental reasons that are fixable, and that when it does fail, that you can detect the failures. Okay, so let's look at how we would handle this mediator problem, okay? These three components with a mediator. So, well, one part of our solution is that the components in Lingua Franca have well-defined interfaces with ports, and instead of where actors reference each other directly, they kind of reach into each other's guts. The components in Lingua Franca don't do that. They have an interface which is ports that accept inputs and ports that produce outputs, and the component itself has no idea what it's connected to. It doesn't have any references to the components that it interacts with. So these ports give you a little bit of a level of indirection. So if you have a component, for example, with two message handlers, let's say this scenario that I described where one of them is going to double an internal state. So this is, this is the actual Lingua Franca code for such a component. We call such a component a reactor. It has two input ports, which are named, have a type. It has a state variable, which has a type and an initial value. And then you define reactions. So there's a reaction to the double input. There's a reaction to the increment input. One of the key things in Lingua Franca is now the inputs are logically time-stamped. So a component like this will always see its inputs in timestamp order. That's guaranteed by the framework. And so now, even if you have messages originating at two different places in the network, the order in which this component sees them is determined by the timestamp, which is a number. Okay, so there's a semantics now to the ordering of the messages. If the timestamps are identical, if there's an event on the double input and an event on the inc input, both with the same timestamp, then in the semantics of Lingua Franca, those will be handled in the order in which these reactions are declared. And consequently, with simultaneous inputs, the doubling will always occur before the increment, guaranteed. And now you can compose this component with a bunch of other concurrent components that can be distributed across a network, and now you have a program with deterministic semantics. So in particular, the composition that I looked at before would have this source of events, this mediator, which could be the vision detection system in the aircraft door example, and the component that handles the messages that come in from the network. And the Lingua Franca code looks like this. We have a main reactor. It instantiates each of these reactor classes, and then it makes connections between their ports, and that's how you write the code to build that application. So how does this preserve determinism? Well, it uses a scheduling policy, which in the case of a distributed system is a non-trivial scheduling policy, right? It's not something you want the application designer to have to build. because it takes a lot of expertise to design these scheduling policies for distributed systems. It's easier for non-distributed systems, but still not trivial, okay? But the key idea is that every event is time-stamped, and every component is guaranteed to see events in timestamp order. By default, every component reacts instantaneously, okay? So if this intermediary component, BAS, is given a time-stamped event at its input, by default, when it reacts, the output has exactly the same timestamp as the input. Okay, so it's logically instantaneous, which means now that if you have this source issuing two requests, a double and an increment request, simultaneously with the same timestamp, this component foo will have two inputs with the same timestamp, and the order in which those will be handled will be deterministic. The doubling will occur before the increment, and you will always get the same result on any implementation of this system. So that is a key part of the art in Lingua Franca, is ensuring this behavior. All right. Now you probably, people in the room, for example, who are familiar with synchronous languages will see this as very familiar. Yes, of course. This is how synchronous languages work. It's also how data flow languages work, okay, which don't have a notion of timestamps. And so there's a lot of history behind using this kind of technique, but it's a very powerful technique. So another part of our solution is, now that we have timestamps, now the timestamps have kind of a key role just preserving determinism. That's useful even if you don't care about real time. You can use Lingua Franca in a way that there's no connection between the timestamps and any physical notion of time. You don't have to connect it to a physical clock. It's about making messages get handled in deterministic order. But once you have timestamps, you might as well use them to get real-time behaviors. So here's an example that was inspired by a paper that Mathieu here was the lead author on about 10 or 12 years ago, some time ago, where he worked with some people from Schneider Electric on a very severely time-constrained real-time problem, which is a protection relay design for a power system that cuts off power to protect equipment when there's been a fault, like a short circuit in a load. And here is a re-implementation of that 10-year-old design in Lingua Franca, with each of the components named as they were in the original paper. And these timers are specifying the rates at which things are going to occur. And for those of you, again, who are familiar with synchronous languages or with time-driven execution or things like that, one of the important properties here is that even though the rates are different, so this particular clock has a period of 555 microseconds, and this clock has a period that is 13,320 microseconds, which I think is, how many times that? 24 times, thank you. Okay, so these are not running at the same rate, but it is really important that the samples be aligned, okay? That a sample seen when this clock is simultaneous with this clock is the sample that corresponds to the one that is produced at that upstream component. This works in Lingua Franca, even in a distributed system. You can put these timer components anywhere in a distributed system, and if they produce events that are logically simultaneous, they have the same timestamp, then any component that receives those events will see them simultaneously, anywhere in the network. Okay? And this is true whether you have synchronized clocks in your network or not. If you do have synchronized clocks in your network, we get a more efficient implementation than without synchronized clocks. But you don't need synchronized clocks to actually implement this correctly. Another aspect in which we introduce timing into Lingua Franca is with this notion of deadlines. You can attach a deadline to a reaction which imposes a physical time bound on when the reaction gets invoked. Now, the interesting thing about this is that this deadline serves two purposes. One is it serves to guide scheduling, because now the scheduler is told that this component that this reaction has a deadline, and consequently, if there's contention for processor resources, the scheduler can give priority to that reaction over something that doesn't have a deadline. But there's a second, perhaps even more important role that the deadline preserves, which is that it gives you a place to put your exception handling code. What do you do when the deadline is violated? Because the fact is that in any real system, stuff happens and things may go awry. And no matter how careful you are with scheduling and with your design of your system, you might find that every once in a while your deadlines get violated. What do? Well, in Lingua Franca, you are required to do something, okay? You have to, in order to specify a deadline, you have to specify a body of code to execute when that deadline is violated. That kind of exception handling is a key property in Lingua Franca. There's also more sophisticated mechanisms for handling more complicated timing relationships that we call the actions, and also for handling aperiodic asynchronous inputs. But I'm not going to go into that detail today. So parallelism. The fact is that a Lingua Franca program, by default, if you run it on a multi-core machine, it uses all the cores. Okay, and it does this in a way that preserves the determinism. So in particular, if you have a design pattern that has a significant amount of parallelism, such as something that's doing a fork join or a scatter gather kind of operation, right? Here's a deliberate design where you have some workload that you can divide up into pieces to execute simultaneously on multiple cores. So in Lingua Franca, this gets specified in using a very compact notation that's due to Christian Menard, the same TU Dresden PhD student who did the AutoZAR work. You can create a bank of reactors, and it's parametrized with some width. And the dependencies between these are explicit in the program, right? The compiler can see that there in fact are no dependencies between the instances in this bank, and consequently there's no constraint to executing these bank components on multiple cores simultaneously. The results of this can be merged into a single port with a style that we call a multi-port. So this is an input with some specified width. And again, the dependence, the messages that arrive all simultaneously, logically simultaneously, not necessarily physically simultaneously, in fact, almost certainly not physically simultaneously, but logically simultaneously, those will be handled in deterministic order. Now, you might think that this kind of parallelism, because of the determinism, would imply a performance cost. You must be giving up some performance to get determinism. Well, Christian Menard proved that that's not the case. We do not give up performance. He compared Lingua Franca head-to-head with state-of-the-art actor frameworks that are both C++ based and Java-based actor frameworks, and found that Lingua Franca sometimes performed better, sometimes performed a little worse, but it was completely competitive with these non-deterministic techniques. The determinism itself, by itself, is not costing us in performance. We also have, in Lingua Franca, an ability to create distributed programs, which are not just executing on multiple cores. The difference is that on a multi-core architecture, we assume a shared memory. Okay, so it's threads that can share memory, and the way that you coordinate things is a bit different than a distributed system where there's no shared memory, and all communication has to happen over the network. So in Lingua Franca, when you want a distributed system, you use this keyword for your main program, federated. You create a federated reactor, and each of the top-level components that you create then will code generate into its own standalone program. And then Lingua Franca synthesizes the code that coordinates those programs and that handles the communication between them. So we call that a federated program. This particular example that's shown on the screen is from a classic paper by Leslie Lamport, where he was actually showing the value of using timestamps for fault tolerance. His emphasis was not on deterministic concurrency. It was on fault tolerance. And he got deterministic concurrency as an accidental side effect of the approach. But in any case, this particular application is a distributed first-come, first-serve access to some shared resource. Okay? So, and in this case, however, there's a little bit of a twist. First-come, first-serve has a very strong semantic meaning in lingua franca. First-come is the request with the earliest timestamp, not the request that arrives earliest on the network. There's a difference. And a key value in having that difference is that your system becomes testable now. Because given some pattern of requests, there is exactly one correct behavior for the system, and consequently you can build regression tests for your system that determine that, in fact, its resource management works. Now, in this case, this kind of coordination does have a performance cost. Okay? So I was claiming that in the multi-core case, determinism doesn't have a performance cost. In the distributed case, there is a performance cost. Okay? And that performance cost is very nicely codified in a very, very trivial result that is due to my colleague at Berkeley, Eric Brewer, called the CAP Theorem. Okay, the CAP Theorem says that if you have a network that breaks, it becomes partitioned, then your system is forced to either give up consistency or give up availability. What does that mean? Well, consistency is agreement on shared values, okay? And in the context of lingua franca, agreement on shared values is a consequence of the determinism of lingua franca. Whenever you have two values that are broadcast from the same point to two different places with the same timestamp, the fact that the components all see the same value with the same timestamp is a consistency property, okay? Availability is about the time it takes you to respond to queries about those values. Okay, so this theorem came up in the database context, and it's a very trivial observation. It says that if your network becomes broken and you access a local copy of your database, and the network's broken, the local copy has two choices. It can either give you a value with no assurance that that value is consistent with the rest of the database, or it can not give you a value and thereby assure that any value it gives you is consistent with the database. But you have no choice. You have to give up one of the two, consistency or availability. And it's a fundamental property of distributed computing. We have generalized and quantified this result, and I could give a whole talk about this because this is, in my view, one of the most interesting things to have come out of the Lingua Franca project. We call it the CAP Theorem because we're not just interested in networks that are broken. The partitioning we replace simply with latency. Every network has latency. A broken network is a network with very long latency, okay? But all networks have some latency, and consistency and availability depend on how much latency you have in your network. And we have derived a numerical relationship between these that has a very beautiful max plus formulation, okay, that enables you, and we've shown actually in this paper that was published just earlier this year, we've shown that the Lingua Franca programming framework gives you a way to explicitly trade these off against one another. So you can choose to relax consistency in order to improve availability. So you improve your response times, better able to meet deadlines, in exchange for a quantified relaxation of consistency in the distributed system, and that this theorem tells you exactly how to relate that to your network properties. So now you can trade these off in any number of ways. So for example, in this aircraft door example, I could say, well, I want the aircraft door to open within 1 second of a request. That's an availability requirement. I can then say, I absolutely require strong consistency. I want to make sure that the open, if there is a disarm command, that the disarm command will be seen at the same time or before the open command. I'm going to insist on strong consistency. So now I have a latency and a consistency requirement. I can derive the network latency I have a consistency and an availability requirement. I can now derive what the network requirements are using this theorem. Okay? Or I can turn that around and use my knowledge of the network properties to derive my availability properties. How much time is it going to take for this actuator to be able to actuate? Okay, so, and the Lingua Franca program gives you a very nice framework to do this kind of reasoning. Another key property of Lingua Franca, which is to me one of the most important ones, is that it is not a programming language. And it has no goal of replacing programming languages. In fact, it complements the programming languages that people use today. So in particular, we call it a coordination language because when you write a reactor, this happens to be a reactor from an aircraft control test case called the Rosas test case, which some of you may be familiar with. It comes from Toulouse. But anyway, the body of the reaction is written in a target language, and currently Lingua Franca supports 5 target languages: C, C++, Python, Rust, and TypeScript. TypeScript is a dialect of JavaScript, and it's quite popular for use in cloud computing kinds of applications. And so the body of the reaction is just written in your familiar programming language. Okay? If you're doing machine learning applications, for example, Python is a go-to choice for many people. Another key part of Lingua Franca is excellent tooling. Okay? I mean, truly excellent. So I'm going to attempt to pop out of PowerPoint and just give you a little example. Okay, so this is the aircraft control system, the Rosas test case from Toulouse. Okay, and we have, as a result of our collaboration with Reinhard von Hangsladen at the University of Kiel in the north of Germany, his team has provided this incredible visualization tool. So this is one of the development frameworks. This happens to be an Eclipse-based IDE, which is the one that I like to use. But anyway, this visualization tool these visualizations are automatically generated when you write the program. So for example, this is the controller for the aircraft. This is, in this particular program, this is the aircraft simulator. You've got the aircraft dynamics modeled in Lingua Franca code. You've got the behavior of an engine, a simulation of an aircraft engine here, okay? And suppose now that I would like to change this program so that, suppose I want to have a redundant controller. So this is a federated program. So each of these components, when I compile this, will generate a separate program that can run on a separate CPU. I'd like a second CPU to execute a replica of the controller. All right, so how to do that? Well, I can just instantiate a new controller. So let me create a second controller. There, I've got my second controller. All right, I can connect the same sources to this second controller. And now I've got 2 redundant controllers. Probably what I would want to do now is create another component that arbitrates between these. And we can create a component that will actually detect failures of the component, because in Lingua Franca, the absence of a message can convey information, particularly in a scenario where you have synchronized clocks. We can actually use the absence of a message to convey information and put in fault handlers that will react to the absence of a message from one of these 2 controllers in some appropriate way. The tool that I just showed you is called Epoch, and it's an Eclipse-based IDE. I think I might be the only one on the team who's actually using that tool, because they all make fun of me. Eclipse, that's antique technology, come on. Get with it, guy. So they tend to prefer the VS Code plugin. So Visual Studio Code is a very, very nice IDE from Microsoft, and it has the same visualization environment built into it. But we also have good old-fashioned command line tools, so it's very easy to use, your own development framework or Emacs or whatever you would like. We also have a very nice interactive web page with good tutorials. It's interactive in the sense that you can choose your target language, and each of the example programs will be different depending on the target language. So if you're doing Python programming, you see the example programs in Python. If you're doing C programming, you see them in C. There's another part of this which I would love to demo, but I'm not going to take the time to do it. But this was due to also our collaborators in Kiel, in particular Alexander Schultz-Rosengarten, who's a PhD student in Kiel in the north of Germany, built a state machine framework within Lingua Franca, where you specify modes of operation for a reactor, and those get visually rendered as this state machine. So this is you may be familiar with this classic sort of instructional control systems problem called the Furuta pendulum. So it's a pendulum that dangles off the end of an arm, right? So there's this dangling pendulum. And the Furuta pendulum control problem is to swing until you get enough energy to swing the pendulum up and then balance it, okay? And it's a pretty challenging control system problem. And in this case, we have 3 modes of operation. There's the swing up mode, where your control laws are trying to impart energy into the pendulum. There's the catch mode, which tries to tamp down the motion of the pendulum. And then there's the stabilize mode, which tries to keep it vertical. And each of these modes, again, is just specified hierarchically using Lingua Franca reactors. There's another aspect of this project that is, I think, very promising, although still pretty early stage. One of the interesting things about Lingua Franca is that even though it embraces languages that are hard to verify, like C and Python, those make many formal verification people run screaming from the room because, they're hard. It's hard to validate programs there. But Lingua Franca has a very nice property, which is that it gives you a very nice separation between the large-scale architecture of your code, which is these reactors that are with a very clean concurrent semantics, versus the low-level imperative code inside of the bodies of reactions. So my PhD student, Saclay Lin, has been pursuing this as an opportunity where you separate out the parts of the verification problem that can use the Lingua Franca semantics from the part that are dependent on the body of the reactions. And one of the nice features about this is that you can have programs now that mix safety critical code that you really do want to be able to analyze with non-safety critical code that you don't really care so much about, that may be too complex to analyze, maybe does things that are just not very suitable to the formal verification. But because of the nice encapsulation of these pieces of code within these reactors, you can analyze a reactor body more or less independently of other reactor bodies, and then use the Lingua Franca semantics to do the composition between these. So a simple demonstration case that he developed, and it's currently in a paper that's under review, is an ADAS application, like the one that I talked about earlier, okay, where you have a combination of sensors from a LiDAR and from a camera here, and then you've got this sensor fusion operation, and you've got this, here's an English language specification for a requirement. So globally, from 0 to 10 milliseconds, this is a quantified temporal logic expression. That you would like within 10 milliseconds, if the LiDAR reaction and the ADAS processor requests a stop at the same tag, the brakes will be applied within 50 milliseconds. That gets translated into a formal temporal logic formula. Actually, Saclay has been exploring taking sentences like this and getting GPT-4 to translate them into this. And it actually does a scarily good job much of the time. It's really astonishing. So anyway, that's part of the work that he's doing. But a big part of this work is also on this idea of being able to do compositional verification, where you can then have a program like this that can have other components in it that are used, for example, to generate dashboard displays and things like that, and you don't really care quite so much at the same level about verifying those components. And those don't become part of your verification problem merely by being part of the same program. So, popping up to the top level, one of the key things about a Lingua Franca program is that it is a model. So the program is a model, and the model is a program. So it's kind of blurring this distinction between modeling and programming. And it's doing this in a way that gives astonishingly good performance. The generated code, we're generating code that we can run on bare iron microcontrollers with very limited amounts of memory using the C target. Okay, we're not doing that with the Python target. That requires a lot more memory. But the C target, very, very low footprint and very high performance. This is the key team. It's scattered around the world. The largest part of it is at Berkeley, but I would say the Dresden people have been really essential to it, and the Kiel people have been equally essential, particularly with the visualization. Martin Schuberl at TU Denmark has been essential to this problem of the very low-level microcontroller targeting. He's kind of our guard point, making sure that we can really do that effectively. The Koreans are doing quite a variety of different things right now, but mostly focused on the distributed computing. It's an active, ongoing project. You can get it open source on GitHub. It's a BSD style license, so amenable, compatible with commercial uses and so forth. So in conclusion, these popular techniques, pub-sub, service-oriented architecture, shared memory, and actors, all have problems, but these are fixable problems. And we think Lingua Franca actually draws elements from each of these, perhaps closest in spirit to the actors, okay? But with the introduction of a deterministic concurrency model, with the addition of a semantics of time that we can relate to physical time, with the ability to do distributed computing as well as parallel computing or multi-core, and with this very nice graphical modeling that really facilitates program development. And there's a pointer to the website, and I'll stop there and take any questions or comments.
Thank you very much, Ivan.